In this video, we're going to talk about derivatives. Before we actually get to the topic of derivative, we're going to talk about velocity so that I could relate it to derivatives so you have more of a concrete example of what a derivative is. All right, when you hear velocity, then you probably think about speed. Okay, our speed, when we're driving in our car, we're thinking miles per hour. And when we think miles per hour, right, we're talking about our distance related to our time. So how many miles we drove in how many hours. And we know that that is a rate. Okay. When we talk about this rate or this speed, then we think about driving on a trip. A lot of times we think about what our average velocity was. What did we average for our speed on this trip? And then we say, oh, my average speed was 70 miles per hour. That was our constant rate of change. Okay, so that was it was still a rate, but as a constant rate because we're talking about it for the whole trip, our average. When we talk about constant rate of change, we're actually talking about a slope. So if we talk about our trip as having an average velocity, then when we're comparing our time and our distance, our average velocity, so we have a constant rate of change, right? We have a line because that's our slope. But that's not really what happens. Instead, when we talk about going on a trip and driving somewhere and comparing our time and our distance, as we're driving somewhere, our distance is going to increase, but at different rates. So we might go slow and then speed up and go faster and then slow down again and maybe even stop. And then we keep driving and faster and slower and faster and slower and however our trip looks. And we could calculate our average velocity, but if we are looking for what our velocity was at a certain specific time or a place, then we're talking about our instantaneous velocity. So let's say right here on our trip, I want to know what our velocity was there. Well, I could find the velocity by looking at that tangent line where it hits at one place. That's what a tangent line is. So if we were to look at that slope of the tangent line to find that instantaneous velocity, what we're actually doing is finding the derivative. So we have to keep that in mind. All right, now you might be asked to look at a graph, create your own graph, or maybe one is provided, and actually figure out what that slope of that tangent line is or that derivative, and you would really just be estimating. So on mine, I know that my tangent line has a positive slope, and it's not super steep, so I might say that it's like 1. When you're estimating, you don't have to get very close. Think more positive, negative, really big number, really small number, right? Is it a number like 1 or 2? Is it more like a number like 1/2, 1/3? We do have some times where our graphs that we have, we won't be able to find a specific tangent line. So you won't be able to find the slope there. So if you look at the first graph at x equals 0, if I were to try to draw a tangent line there or ask everybody to draw one, you may all draw different. You might draw one here, you might draw one there, draw one there. All right, so those are our tangent lines. So we can't just draw one, so there is not one specific slope, so we can't find the derivative there. Same thing at x equals 0 for the next one. If I were to try to draw one tangent line, everybody might draw some different line right there at x equals 0. And for this last graph at x equals 1, we have an issue because which point are we even looking at? So where would I draw my tangent line? So please just keep in mind that when we are asked to find the derivative at a point, what we're doing is we're finding the slope of the tangent line at that specific place. You aren't always going to be asked to find the derivative from a graph, though, or to find the slope of the tangent line. We can actually find the derivative algebraically using this formula and this definition. So the derivative of a function at x equals a, so at a specific point on the graph, is this formula. Now you actually say this is f prime of a. That's for the derivative. We use that prime symbol. So to find the derivative of a, or f prime of a, we do the limit as h approaches 0, and we will use the letter h in our equation, in our formula, of f of a plus h. So we're going to plug in a plus h into the function, minus f of a, we'll plug in whatever a is, whatever the number is, all over h. And we will use that to find the derivative. Let's try one. Okay, so we're going to find f prime of 4, or the derivative of the function at 4. So I'm going to write down my formula again. So when we find f prime of 4, we have the limit as h approaches 0 of f of, and we're going to be plugging in 4 plus h minus f of 4 all over h. So the limit as h approaches 0 of, okay, now we're going to plug in 4 plus h into the function. So anytime there's an x, it gets replaced with 4 plus h. So 2 times 4 plus h squared minus 3. Okay, so that's, we did f of 4 plus h, and then minus, and now we're going to do f of 4. Okay, so we've got this other function. I like to use a different color. We're going to do minus f of 4. So be careful, there's a minus sign, so I'm going to use a parenthesis because there could be more than one piece here. So plug in 4 for the function. So 2 times 4 squared minus 3. All over h still. All right, so the limit as h approaches 0. And please keep in mind, in this whole thing, we're going to be finding the limit of this thing we're simplifying, which means if we could just use direct substitution by plugging in 0 for h, we would do that, but we'd get 0, and we have 0 in the denominator right now, so we can't. All right, so we're simplifying. We need to do 4 plus h squared. So 4 plus h times 4 plus h is 16 plus 8h plus h squared. Still have minus 3, minus, and if we were to do the parentheses, we'd get 29. Okay, still all over h. So the limit as h approaches 0, got to distribute that 2, so 32 plus 16h plus 2h squared minus 3 minus 29, still all over h. All right, so let's try to simplify. I've got 32 minus 3 minus 29. 32 minus 3 is 29 minus 29, so it looks like those cancel. So I have the limit as h approaches 0 of 16h plus 2h squared all over h. Well, I still need to simplify, and I notice the two top parts have a greatest common factor of h. So I'm going to factor out h. And I notice that the h's will cancel. So we have the limit as h approaches 0 of 16 plus 2h, and now that the h is gone from the denominator, you can plug in 0 for h, and you get 16. So we found that f prime of 4, or the derivative of the function at 4, is 16. So if you were to graph 2x squared minus 3, and you were to locate where x equals 4 and draw a tangent line, the slope of that tangent line would be 16. All right, so we found the derivative at a specific point A, but we might have to find the derivative for the whole function, so for any value of x. So if you notice, it's almost the exact same formula, right? Wherever the a was, there's now an x. So this was an a and this was an a, but now it's just x. So let's find the derivative of this new f function, so f of x equals x squared, for x. Okay, so the derivative at x. All right, so the limit as h approaches 0, I already have my formula up here. So let's plug in x plus h. So I'm plugging in x plus h into this function. So x plus h squared minus, now I'm going to plug in, well, I'm plugging in x for the function, so it stays exactly the same. Still all over h. So we have the limit as h approaches 0, you got to do x plus h squared. X plus h times x plus h is x squared plus 2xh plus h squared. Still have minus x squared all over h. Got to keep that all over h because that's the problem. That's why we can't plug in 0 yet. Now the x squared minus x squared cancels. So we have the limit as h approaches 0 of 2xh plus h squared all over h. Yet again, greatest common factor at the top is h. Factor it out. And the h's cancel. So we have the limit as h approaches 0 of 2x plus h, plug in 0, you get 2x. So we found the derivative of the function is 2x. And now that means I could find the derivative of our function at any value of a by just plugging it in. So if I were to ask you, what's f prime of 1, or the derivative at 1, then you could just plug in 1 for that derivative, and you would get that it's 2. So please remember that if they ask you to find the slope of the tangent line, okay, so not the slope of the graph, but the slope of the tangent line of the graph, then what it's really asking you to do is to do the derivative, and vice versa. If they ask you to find the derivative, you're finding the slope of the tangent line.